A star dies in a flash of light brighter than 1 billion suns. We are traveling to the galactic graveyards it leaves behind, haunting regions where the ghosts of stars linger. By the end, you will understand how these cosmic tombs are responsible for your very existence. We will explore how a stellar corpse can weigh more than a mountain, and why some dead stars have magnetic fields strong enough to erase a credit card from halfway to the moon. What forgotten story does a dying star tell about our own beginnings? A star's life is a story written by gravity and fire. Deep within a stellar nursery, immense clouds of gas and dust slowly collapse under their own weight, a celestial cradle like the Orion Nebula. For millions of years, this material contracts, spinning and heating until the core becomes so incredibly dense and hot that it triggers the cosmic engine of nuclear fusion. Hydrogen atoms are forged into helium, releasing a flood of energy that makes the newborn star shine. This is the moment a star is truly born, beginning a long equilibrium where the outward pressure from fusion perfectly balances the relentless inward crush of gravity. This delicate truce can last for billions of years, but it cannot last forever. The ultimate fate of the star, and the kind of ghost it will leave behind, is sealed by its mass from the very beginning. A modest star like our own Sun will burn steadily for about 10 billion years. When its nuclear fuel is finally depleted, its outer layers will gently drift away, forming a beautiful, glowing shell of gas called a planetary nebula. At its heart, only a dense, Earth-sized core remains, a white dwarf. But for stars many times more massive than the Sun, the end is far more spectacular and violent. Their immense gravity demands a fiercer, faster burn, consuming their fuel in just millions of years. When their core can no longer support itself, the balance of its entire life shatters in an instant. The inward pull of gravity wins the final battle, and the star collapses catastrophically, setting the stage for one of the universe's most powerful events, a supernova explosion. This is not an end, but a violent rebirth, a transformation that scatters the star's enriched remains across the galaxy, seeding future generations of stars, planets, and life itself. That final collapse happens with staggering speed. In less than a second, the star's iron core, a sphere the size of Earth, crushes itself into a ball of neutrons just a few miles across. The energy released in this instant is almost beyond comprehension, launching a shockwave that races outward and literally tears the rest of the star to pieces. This is the supernova, a single stellar explosion that can briefly outshine every other star in its entire galaxy combined. For a few glorious weeks, it radiates more energy than our Sun will over its entire 10 billion-year lifespan. Within this cosmic forge of unimaginable heat and pressure, atoms are slammed together with such force that they create every element in the universe heavier than iron. The gold in a wedding ring, the mercury in a thermometer, the uranium in a power plant, all of it was born in the heart of a dying star. Then, the explosion hurls this newly forged material outward at millions of miles per hour, a glittering cloud of stellar guts expanding into the void. We have seen this celestial drama play out in our own skies. In the year 1054, Chinese astronomers recorded a guest star so bright it was visible in the daytime for weeks. Today, we know they witnessed the supernova that created the Crab Nebula, a beautiful, tangled web of gas still expanding from that ancient detonation. This is the ultimate purpose of the star's violent death, to seed the cosmos with the raw ingredients for new worlds. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was once scattered by such an explosion. Every one of us is literally made from the ashes of long-dead stars, and in the wake of this cataclysm, as the brilliant light of the supernova fades, it leaves behind the true ghost of the star, an incredibly dense and bizarre object where the laws of physics are pushed to their absolute limit. These supernova remnants are the star's final breath made visible, vast glowing shrouds that can stretch for dozens of light years. For thousands of years after the explosion, this expanding shell of stellar debris rams into the surrounding interstellar gas, sculpting it into the beautiful, intricate nebulae we see through our telescopes. The Cygnus Loop, a faint, filmy veil of light in our night sky, is one such ghost, the fading echo of a star that died somewhere between 10 and 20,000 years ago. Within these chaotic clouds, the physics is extreme. The forward blast wave of the remnant acts like a cosmic snowplow, pushing gas ahead of it and heating that material to temperatures of millions of degrees, causing it to glow with intense X-ray light. These same shockwaves are also nature's most powerful particle accelerators, boosting cosmic rays, which are mostly protons and atomic nuclei, to nearly the speed of light. Inside this churning cauldron, the heavy elements forged in the supernova itself are stirred and mixed with the surrounding space. Oxygen, silicon, and iron are scattered like seeds, enriching the galactic environment with the very stuff that will one day coalesce into rocky planets and perhaps living organisms. By carefully measuring how fast these remnants expand, and by observing light echoes, which are reflections of the original explosions flash off of distant dust clouds, astronomers can rewind the cosmic clock. They can pinpoint the exact year a star died, centuries or even millennia after the event itself was witnessed from Earth. The delicate, glowing tendrils of a supernova remnant are a beautiful lie, masking the unimaginable violence of their birth. They are a lasting monument to destruction that is also an act of creation, and at the very heart of this beautiful, expanding monument, where the star once was, lies the compressed core that survived the blast, an object of even greater mystery. At the heart of that beautiful, expanding remnant lies the supernova's final, compressed prize. If the collapsing core is between 1.4 and 3 times the mass of our Sun, gravity forges it into one of the universe's most extreme objects, a neutron star. All that immense stellar mass is crushed into a sphere no wider than a city. This creates a density so fantastical it defies all earthly experience. A single sugar cube's worth of this material would weigh not just tons, but billions of tons, a mass equal to every person on our planet combined, compressed into a tiny speck. This happens because gravity wins its ultimate victory, squeezing the atoms themselves out of existence. Electrons are forced into protons, and everything fuses into a solid ball of neutrons, a single atomic nucleus the size of a metropolis. The only thing preventing this cosmic marble from collapsing further into a black hole is a bizarre quantum rule called neutron degeneracy pressure, a last-ditch atomic stand against the infinite crush of gravity. The first hint that such strange objects were real came not from a visible image, but from a sound, a rhythmic pulse. In 1967, a graduate student named Jocelyn Bell Burnell detected a radio signal from deep space that ticked with a precision far greater than any human-made clock. This was the first pulsar, a rapidly spinning neutron star. As these stellar corpses rotate, they beam intense radiation from their magnetic poles, and if that beam sweeps across Earth like a cosmic lighthouse, we observe it as a perfectly timed pulse. Some pulsars spin hundreds of times every single second, their dizzying speed a testament to the conservation of a star's original spin. now concentrated into this tiny, furious object. But even these are not the most violent neutron stars. That title belongs to the Magnetars. These are neutron stars born with magnetic fields so powerful they defy metaphor. A magnetar's magnetic field is 1,000 trillion times stronger than the field that guides a simple compass on Earth. If a magnetar were located as far away as our moon, its magnetic field would be strong enough to erase the data from every credit card on the entire planet. These unimaginable forces stress the star's rigid crust, causing colossal starquakes that snap magnetic field lines. In a fraction of a second, such an event can release more energy than our sun, will emit over 100,000 years, a flash of gamma rays that can temporarily outshine every other source in the galaxy. Neutron stars are the ultimate laboratories, places where matter is pushed into states we cannot recreate, and where the very laws of physics are tested to their breaking point. Their existence shows us just how far gravity can go in warping reality, yet they are merely the gatekeepers to an even deeper mystery. These cosmic lighthouses, known as pulsars, are perhaps the most mesmerizing ghosts in the galactic graveyard. They are neutron stars in motion, spinning at dizzying speeds and firing twin beams of radiation from their magnetic poles. When that lighthouse beam sweeps across our line of sight here on Earth, we see a flash, a pulse of energy that repeats with a rhythm more precise than any human-made clock. The discovery of the first one, PSRB 1919+21, was a moment of genuine astonishment. A young graduate student named Jocelyn Bell Burnell noticed a signal in her data that pulsed with such perfect regularity that her team half-jokingly labeled it LGM-1 for little green men. It was not aliens, of course, but something almost as strange, a new type of celestial object that challenged everything we thought we knew about the stability of stars. This incredible regularity is their defining feature. The spin of a pulsar is so unwavering that it surpasses the accuracy of the atomic clocks we use to define time on our planet. This has made them extraordinary tools for science. Astronomers have used these ticking clocks to perform some of the most stringent tests of Einstein's theory of general relativity, observing how the fabric of spacetime warps around them with a precision we could never achieve in any laboratory on Earth. Perhaps the most famous example is the Crab Pulsar, the furious heart of the Crab Nebula. This is the remnant of the very supernova witnessed in the year 1054, and its core is still spinning 30 times every single second. That rapid rotation generates a powerful wind of particles that energizes the entire nebula, causing the surrounding gas to glow brilliantly, a ghost powered by its own relentless heartbeat. This connection makes them more than just curiosities. They are potential navigational beacons for a future of interstellar travel, and they act as natural probes, their signals subtly altered as they pass through the clouds of gas and dust between the stars. Every single pulse is a direct echo of the supernova's collapse, the last will and testament of a star that refused to go quietly, its ghostly heartbeat ticking away for millennia in the vast silence of space. But for some neutron stars, the magnetic field is the true source of their haunting power. These are the Magnetars, the universe's ultimate magnetic monsters. They belong to a rare and volatile class of neutron stars, distinguished by magnetic fields of such staggering strength that they defy all comparison. A magnetar's field is 1,000 trillion times more powerful than Earth's. At a distance halfway to the moon, that field would be strong enough to warp the very structure of the atoms that make up your body. This unimaginable force is generated in the chaotic first seconds of the star's birth, as the collapsing core of a massive star spins at an incredible rate, stirring a dynamo of superfluid neutrons in its interior. The energy stored within this twisted magnetic prison is almost beyond calculation, and it is this pent-up power that makes magnetars so spectacularly unstable. Their solid crust, a crystalline lattice of iron under immense pressure, is constantly stressed by the magnetic field trying to break free. This tension builds until the crust can no longer contain it, cracking in a starquake of cosmic proportions. In a fraction of a second, this seismic event can release more energy than our Sun will emit over 100,000 years. We have felt the reach of these distant monsters. In December of 2004, a magnetar named SGR 180620, located 50,000 light-years away, unleashed a flare of gamma rays so intense that, for a fifth of a second, it actually outshone every other star in our own Milky Way galaxy combined. The pulse of radiation was so powerful that it compressed Earth's magnetic field and violently ionized the upper atmosphere, a clear signal received from halfway across the galaxy. This twisted magnetosphere creates an environment so extreme that atoms themselves are stretched into long, needle-like rods, unable to maintain their normal shape. Yet this fury is short-lived. A magnetar's terrifying magnetic field decays relatively quickly, its energy spent in these violent outbursts. After only about 10,000 years, the monster falls silent, becoming just another, more ordinary neutron star. The explosive life of a magnetar proves that a star's death is not always a quiet surrender. For some stellar remnants, death is a state of perpetual, violent activity, a final, furious storm before the long, dark quiet. And this leads us to the final, most absolute ghost in the graveyard, the point where even light itself cannot escape. Yet even a magnetar's fury is a temporary storm, a final tantrum before the long quiet. For the very largest stars, death is not a transformation into a new state of matter, but a complete and total surrender to gravity. When the collapsing core of a dying star weighs more than about 3 times our Sun, no force in the universe can save it. Not the fierce pressure of degenerate neutrons, not the strength of atomic bonds, nothing. The collapse does not stop. It continues until the very fabric of space and time is punctured, creating the ultimate gravitational tomb, a stellar mass black hole. This is a region where gravity becomes an absolute prison. The boundary of this prison is called the event horizon, a spherical point of no return. Once anything, even a single photon of light, crosses that invisible threshold, it can never come back. The star has effectively vanished from our observable universe, leaving behind only its immense gravitational pull as a ghostly signature. We cannot see these black holes directly, for they emit no light. Instead, we find them by watching the agony of other stars. Many stellar mass black holes exist in binary systems, locked in a gravitational dance with a living companion star. The black hole's immense gravity acts as a cosmic vampire, slowly pulling streams of gas from its partner. This stolen material does not fall straight in. It spirals inward, forming a superheated, whirling disk around the black hole, a vortex of doomed matter known as an accretion disk. Friction within this disk heats the gas to temperatures of millions of degrees, causing it to glow with intense X-rays, a final scream of light before it is silenced forever at the event horizon. The first such object to be confirmed was Cygnus X1, a powerful and variable source of X-rays in our galaxy. For years, astronomers debated what it could be, with Stephen Hawking famously making a bet that it was not a black hole. He later conceded as the evidence became overwhelming. The precise orbit of the visible star revealed it was circling an invisible companion far too massive to be a neutron star, a dark anchor with a gravitational grip that could only belong to a black hole. At the very center of this gravitational maelstrom, according to our current laws of physics, lies the singularity. This is the crushed remains of the star's entire core, collapsed into a point of infinite density. a place where the laws of general relativity break down and our understanding of the universe ends. The silent, dark presence of a stellar mass black hole is the most profound grave imaginable. It is a monument to a star that has been so utterly erased by its own weight that it becomes a permanent question mark in the cosmos, a place where space and time themselves are tied into a knot from which there is no untying. This intricate anatomy of a supernova remnant is a cosmic engine driven by two powerful and opposing shock waves. The forward shock is the leading edge of the explosion, a supersonic wall of energy that plows directly into the cold, undisturbed interstellar medium. This is the celestial snowplow, violently sweeping up and compressing the thin gas that floats between the stars. The collision is so intense that it heats this material to staggering temperatures of millions of degrees, causing it to glow not in visible light, but in high-energy X-rays. This is the brilliant, ethereal halo we observe with space telescopes like Chandra, a testament to the raw power still coursing through the nebula. Yet racing in the opposite direction, back toward the remnant's heart, is the reverse shock. This wave travels inward through the expanding cloud of stellar debris, the material that was violently ejected from the star itself. As this reverse shock slams into the ejector, it heats it to a lower but still immense temperature, making it glow brightly in the optical light our eyes can see. The beautiful, filamentary structures we admire in images of the Crab Nebula are largely the product of this reverse shock, illuminating the corpse of the star from the inside out. Between these two great shock fronts lies a turbulent boundary known as the contact discontinuity. This is where the two rivers of material meet, where the supernova's own enriched ejector violently churns and mixes with the swept-up interstellar gas. This chaotic cauldron is a primary site for galactic recycling, stirring and dispersing the heavy elements forged in the star's death throes, seeding the galaxy with the iron, oxygen, and silicon necessary for new planets and life. This entire system, this dynamic bubble of opposing forces, acts as one of nature's most powerful particle accelerators. The shock waves provide a tremendous boost of energy, trapping protons and atomic nuclei and flinging them to nearly the speed of light, creating the cosmic rays that constantly bombard our galaxy. The shape and evolution of the remnant, whether it forms a perfect sphere or a twisted knot, is dictated by the complex interplay of these shocks and the environment into which the star died. By learning to read this anatomy, by studying the X-ray glow of the forward shock and the optical light from the reverse, astronomers can perform a kind of cosmic autopsy. They can measure the total energy of the original blast and decode the exact chemical composition of the star's final breath, a story of destruction and creation written in the ever-expanding debris. That beautiful, intricate anatomy of a supernova remnant is far more than a cosmic spectacle. It is a vital factory for the very building blocks of life. The immense heat and pressure within the explosion itself serve as the universe's primary forge for creating the heaviest elements in existence. During the star's life, it could only fuse elements up to iron, but the cataclysm of its death provides the extreme environment necessary for something called the R process, or rapid neutron capture. In a furious blizzard of neutrons lasting mere seconds, atomic nuclei are bombarded and built up into heavier and heavier forms. This is how the gold in a wedding ring, the silver in photographic film, and the uranium that powers reactors are born. They are not ancient relics from the Big Bang, but rather they are the freshly minted currency of stellar destruction. This newly forged material, along with all the oxygen, carbon, and iron the star created during its lifetime, is then violently blasted outward. The expanding remnant acts as a cosmic delivery service, hurling these enriched stellar guts across light years of space. There, they mix with the thin gas and dust drifting between the stars, seeding vast molecular clouds with the ingredients for new solar systems. We have direct proof that our own solar system was born from such an enriched cloud. Ancient meteorites that have fallen to Earth contain traces of specific radioactive isotopes like aluminum-26, which have very short half-lives. The only plausible explanation for their presence in our primordial solar nebula is that a nearby supernova exploded, injecting these fresh elements into our stellar nursery just before the Sun and planets coalesced. This means the iron that carries oxygen in your blood, the calcium that strengthens your bones, and the oxygen you are breathing right now were all forged in the heart of a star that lived and died billions of years ago. That star ended its life in a spectacular fireball, scattering its elemental legacy across the galaxy, a legacy that eventually found its way into you. This continuous cycle of star birth, death, and rebirth is the engine of galactic evolution. It transforms simple hydrogen and helium into the rich diversity of elements that make rocky planets, oceans, and life itself possible. We are not just observers of these distant galactic graveyards, we are their living product. We are stardust that has coalesced into conscious form, a temporary assembly of atoms given a moment to look back at the cosmic cycles that created them. The stories of these stellar deaths are not locked away in ancient light, they are written in human history. For a handful of supernova, the moment a star died was witnessed by our ancestors and recorded for posterity, creating a profound link between our world and the cosmos. In the spring of the year 1006, a new star appeared in the southern sky that was so dazzling it stunned observers across the globe. Astronomers in China, Egypt, Iraq, and Japan, and even Swiss monks and Native Americans in Arizona, all wrote of a brilliant, point-like light that rivaled the quarter moon. It was visible in broad daylight for weeks and cast shadows at night for months. Modern science has identified this as SN 1006, likely the brightest supernova in recorded history, the result of a white dwarf star being utterly annihilated. Its remnant today is a faint, expanding shell of gas, a direct match to those thousand-year-old descriptions. Just 48 years later, in 1054, another star exploded in our galaxy. Chinese court astronomers called it a guest star, visible in the daytime for 23 days and at night for nearly 2 years. This was the birth of the Crab Nebula, and its description was so precise that we can pinpoint the exact cloud of debris it refers to. There is even tantalizing evidence that ancestral Puebloan people in what is now the American Southwest painted the event, a star next to a crescent moon, matching the recorded position of the supernova near our own moon. Then came 2 more brilliant events that shook the very foundations of human understanding. In 1572, the Danish nobleman Tycho Brahe observed a new star in the constellation Cassiopeia. At a time when the heavens were believed to be perfect and unchanging, Tycho's meticulous observations proved this object was far beyond the moon, a real change in the immutable realm of the stars. His supernova challenged the Aristotelian worldview to its core. Just 32 years after that, in 1604, Johannes Kepler observed his own supernova, further dismantling the old dogma and helping to ignite the scientific revolution. These historical sightings are more than just ancient curiosities. They are crucial data points that allow us to study the entire life cycle of a supernova remnant, from its brilliant first second to its faded, expanding ghost thousands of years later. They prove that the sky is not a static painting, but a living, breathing, and sometimes violent entity. And while some ghosts announce their presence with a flash of light that echoes for centuries, others hide in plain sight, their true nature completely invisible to the human eye. These historical sightings, brilliant as they were, only captured a fraction of the story. The true nature of a galactic graveyard is often completely invisible to human eyes. To see the full phantom, we must learn to see with different senses across the entire electromagnetic spectrum. Many of the most fascinating remnants emit little to no visible light, hiding their secrets in wavelengths we cannot naturally perceive. It is only by combining the views of many specialized telescopes that we can assemble a complete portrait of these stellar tombs. Radio telescopes, like the sprawling Very Large Array with its collection of dish antennas, listen for a specific kind of signal called synchrotron radiation. This is the faint radio whisper emitted by high-energy electrons spiraling at nearly the speed of light through the remnant's tangled magnetic fields. This radio view maps out the ghostly skeleton of the remnant, tracing the long, thin filaments where its energy is most concentrated. It reveals the intricate structure of the magnetic cage that holds the entire nebula together. To see the heat of the explosion itself, we turn to X-ray observatories like Chandra and XMM Newton. These telescopes detect the fierce glow of gas that has been heated by the supernova's shock waves to temperatures of millions of degrees. The brilliant X-ray light shows us the hottest and most violent regions of the remnant, the places where the blast wave is still actively slamming into the interstellar medium, a celestial fire that is still burning. Meanwhile, infrared telescopes like Spitzer and Herschel act as cosmic dustbusters. They peer straight through the obscuring clouds of dust to see the cooler material within the debris. This infrared vision reveals where the expanding cloud of heavy elements is beginning to cool and condense, sometimes even forming new, complex molecules on the ashes of the old star. It shows us the raw material for future planets starting to coalesce within the destruction. And at the very highest energies, gamma-ray instruments like the Fermi Space Telescope capture the death rattles of the remnant. They detect photons produced when the accelerated cosmic rays, those protons and atomic nuclei boosted to incredible speeds, finally collide with other particles. Each part of the spectrum tells a different chapter of the same story. Peering into these different wavelengths is like using every sense to explore a haunted house. Your eyes might see a dusty, empty room, but a radio receiver hears the faint echo of a voice in the walls. An infrared camera shows the cold spot where a presence stands, and a gamma-ray detector feels the residual energy of a sudden, violent event. By combining these views, astronomers do not just see a cloud of gas. They can read its temperature, its composition, its magnetic field, and its motion. They can witness the ongoing synthesis of new elements and track the paths of the universe's most energetic particles. This multi-wavelength approach is our only way to find the most recent stellar deaths, the ghosts that have not yet had time to cool and fade, and to understand that a galactic graveyard is not a silent, static place, but a dynamic and ongoing chemical factory. The last time a star exploded within our own Milky Way galaxy, Galileo was still perfecting his telescope. Kepler's star of 1604 was the final such event recorded in our galactic neighborhood, leaving a 4-century-long silence. But this does not mean the galaxy is dormant. Astronomers now discover supernova in distant galaxies almost weekly, yet the hunt for one within our own spiral arms is a central pursuit of modern astronomy. They have turned the entire sky into a crime scene under constant surveillance, using automated robotic telescopes that scan the heavens night after night, comparing digital images to spot any new point of light that dares to appear. The next galactic supernova could ignite at any moment, and when it does, we will not see it first. We will hear it deep underground, in vast tanks of ultra-pure water shielded from cosmic interference, lie neutrino observatories like Super and in Japan. In the very first second of a core collapse supernova, when the star's iron core collapses into a neutron star, 99% of the energy is carried away by a flood of these ghostly particles. Trillions of neutrinos would pass effortlessly through the Earth, but a precious few would be captured in these subterranean detectors, sounding a global alarm. This gives astronomers a priceless heads-up, a few hours of warning before the shockwave finally tears through the star's surface and the optical light floods our skies. That alert would trigger the most intense observing campaign in history. Every telescope on Earth and in space, from radio dishes to gamma-ray detectors, would swivel to target the dying star. We would witness the explosion's very first light, track the rising fireball in real time, and watch as a new supernova remnant is born before our eyes. The scientific value would be immeasurable. For the first time, we could directly test our models of how a star actually tears itself apart. We could study the properties of neutrinos streaming directly from the heart of the collapse, and we could watch in real time as a neutron star, or perhaps even a black hole, takes its first gravitational breath. And for all of us, it would be a celestial spectacle unseen for over 400 years. A new star would blaze in the night, possibly rivaling the full moon and casting shadows, a brilliant pinprick of light that could even be visible in the daytime for weeks. This is the event astronomers dream of, a cosmic lottery ticket waiting to be cashed. It is a powerful reminder that our galaxy is a living, evolving system, and its graveyards are not just monuments to the past, but active construction sites for the future. A galactic graveyard is far more than a collection of tombs. It is a vibrant engine room for the entire galaxy. These supernova remnants are the great recyclers and regulators of cosmic ecology, their influence stretching far beyond their own glittering borders. The shock waves that sculpt their beautiful forms do not simply fade away. They travel for thousands of light years, plowing into the cold, quiet clouds of gas that drift between the stars. This violent interaction is a fundamental form of galactic feedback. The immense energy from the blast heats the surrounding interstellar medium, preventing it from cooling and collapsing too quickly. It also stirs the gas, churning the galactic pot and creating the dense, turbulent knots where gravity can finally take hold and ignite the birth of new stars. In this way, a star's death does not just provide the raw materials for new worlds, it also provides the spark that begins the construction process. This is a cycle of controlled chaos. When a massive star cluster reaches the end of its life, it can unleash a coordinated salvo of supernova. Their collective shock waves and stellar winds merge, carving out colossal cavities in the galactic disk known as superbubbles. These are vast structures, hundreds of light years across, filled with incredibly hot, thin gas that has been blown clear by successive explosions. These superbubbles shape the very architecture of a galaxy like our Milky Way, and their energy can be so immense that it punches clear through the galactic disk, launching fountains of million-degree gas high above the plane of the galaxy. This process is crucial for the long-term health of a galaxy. By constantly stirring the galactic gas and even ejecting some of it into the halo, supernova prevent a galaxy from consuming its entire fuel reserve in one frantic burst of star formation. They act as a cosmic throttle, regulating the rate at which new stars are born and ensuring that the galaxy's gas supply lasts for billions of years. Without this violent feedback mechanism, a galaxy would burn through its fuel in a short, brilliant firestorm, leaving behind a quiet, aging system devoid of the ongoing activity needed to forge heavy elements and create rocky planets. Our own existence is a direct consequence of this delicate balance. The supernova that seeded our solar system did not just provide the iron for Earth's core and the oxygen for our air. It was part of a grand, self-regulating cycle that made such a stable, long-lived planetary system possible in the first place. The ghost of a dead star is therefore not an end, but a persistent, shaping hand, a force that guides the evolution of its entire galactic home, transforming graveyards into the very cradles of cosmic renewal. A perfect sphere of destruction is a beautiful idea, but the universe rarely deals in perfection. When we point our most powerful telescopes at relics like Cassiopeia A, we do not see a smooth, round bubble. Instead, we witness a chaotic, tangled wreckage, a field of shrapnel where colossal jets of material punch out in opposing directions and vast, lumpy clumps of gas defy any sense of order. This jagged asymmetry is not a flaw in the design, it is the central clue to how a star actually dies. The explosion itself is fundamentally lopsided. Deep within the collapsing star, the rebirth of the shockwave is a battle against chaos. A phenomenon known as the standing accretion shock instability causes the nascent shock to stagger and wobble violently, like a top about to fall over. This wobble creates a lopsided detonation that rips the star apart unevenly, favoring one direction over another and hurling debris in an imbalanced fury. For some stars, their final moments are even more focused. If the progenitor star was spinning rapidly or possessed a powerful magnetic field, its death can be channeled. The entire explosive force gets focused into two narrow beams erupting from the poles, much like a welder's torch. This creates a breathtaking hourglass shape in the remnant, a structure born from the star's own internal dynamics. These violent imperfections have a profound consequence for the stellar corpse left behind. The same asymmetry that shreds the star also acts like a rocket engine, giving the newborn neutron star a powerful kick. This is why we find these cosmic marbles racing through space at hundreds of thousands of miles per hour, runaway ghosts ejected from their own birthplaces. The lopsided debris field is therefore a frozen moment, a direct snapshot of the turbulent forces that shattered the star's core. To understand why a star explodes, we must first understand why it explodes so messily. Every jagged filament and every off-center jet is a piece of the puzzle, a testament to the fact that a star's death is not a clean, symmetrical burst, but a chaotic, stumbling collapse that forever scars the remnant it leaves behind. Our own sun will meet a far gentler end than the cataclysmic explosions we have witnessed. It is a star of modest mass, destined not for a supernova but for a quiet, almost poetic transformation. In roughly 5 billion years, the sun will exhaust the hydrogen fuel in its core. With the outward push of fusion waning, gravity will begin to win its long battle. The sun will swell dramatically, cooling as it expands, becoming a red giant so vast that its outer layers will engulf the orbits of Mercury, Venus, and likely even Earth. The inner solar system will be scoured clean, a stark reminder that even a peaceful stellar death is absolute for the worlds too close to the fire. Then, in a final, gentle act, the dying star will shrug off its outer atmosphere entirely, casting a magnificent shell of incandescent gas out into the void. This expanding shroud will form a planetary nebula, a brief, jewel-like spectacle in the galactic dark. For tens of thousands of years, this cloud will glow, illuminated not by the violence of a shockwave, but by the fierce ultraviolet light of the star's exposed core. That core, no longer supporting fusion, will collapse under its own weight until a bizarre quantum force called electron degeneracy pressure halts the crush. This is the birth of a white dwarf, an object with the mass of a star packed into a volume the size of Earth. A single teaspoon of this material would weigh many tons, a dense cinder of carbon and oxygen. Famous objects like the Ring Nebula and the Helix Nebula are perfect examples of this fate, their intricate, glowing patterns serving as beautiful tombstones for stars that lived and died without a final, violent scream. This quiet departure still contributes to the galaxy's chemical richness. During its red giant phase, the Sun will forge heavier elements like carbon and nitrogen in its core, then dredge them up to the surface. When the planetary nebula is expelled, it carries these newly created elements into the interstellar medium, seeding future generations of stars and planets with the building blocks of life. The white dwarf left behind is a monument to stability, but it is not eternal. With no internal energy source, it will simply radiate its leftover heat into space over trillions of years, slowly fading from white-hot to red, and eventually to a cold, dark black dwarf, a diamond-like ghost in the cosmic graveyard. This peaceful fate is the most common in the universe, a reminder that not all stellar deaths are violent, but all of them, in their own way, give something back. Yet even in our most detailed maps of these stellar graveyards, some of the most important graves are simply empty. For a handful of well-studied supernova remnants, the dense, spinning heart of the dead star is nowhere to be found. Take the expanding cloud of debris from Tycho's supernova, the very star that shocked the world in 1572. We see the beautiful filamentary shell, the echo of that brilliant light, but at its center there is nothing. No pulsing radio beacon, no glowing hot spot, just a profound and puzzling silence. This absence is a genuine cosmic mystery, and astronomers have several compelling theories for where these neutron stars have gone. Perhaps the most dramatic explanation is that the star's death was so violently lopsided that the newborn neutron star received a tremendous kick, a gravitational slingshot that launched it away at incredible speed. In this scenario, the stellar corpse is not hiding, it is fleeing, a rogue pulsar racing through the darkness of interstellar space, already far beyond the gaseous tomb it left behind. We have actually found such runaway neutron stars, like the Guitar Nebula pulsar, streaking through space so fast it creates a bow shock in the interstellar gas that looks like the shape of a musical instrument. Another, quieter possibility is that the neutron star is still there, right in the center of the remnant, but it has simply failed to introduce itself. A pulsar's lighthouse beam is narrow, and if that beam does not happen to sweep across our line of sight from Earth, the star remains invisible to our radio telescopes. It would be a silent, dark cinder, its rapid spin and powerful magnetic field completely undetectable to us. There is a third, more final possibility. Perhaps the explosion itself was a fizzle, a failed attempt to blow the star apart. In this case, the collapsing core might have been so massive that even a neutron star could not support it, and it continued its catastrophic collapse, plunging past the point of no return to become a black hole. The evidence for this would be the utter lack of any central object, a void where a spinning heart should be. The search for these missing compact objects is a major astronomical pursuit. It involves using the most sensitive X-ray telescopes to look for the faint, pinpoint glow of a hot neutron star that is not pulsing, or scanning for the subtle, wispy cloud of a pulsar wind nebula, the telltale bubble of particles that would be blown by a hidden, spinning magnet. Each empty remnant is a crime scene without a body, and the clues left behind force us to refine our understanding of how these colossal explosions actually work. The properties of the neutron star, or the nature of its absence, tell us about the kick it received, the spin it was born with, and the ultimate success or failure of the supernova mechanism itself. This search reminds us that for all we have learned, the galactic graveyard still holds profound secrets, and the most important ghosts are often the ones we cannot see. The silent ballet of a supernova remnant is a performance written in light, but we are now learning to hear its music. astronomers have begun a remarkable process called sonification, translating the raw data from objects like the Tycho Supernova Remnant into sound. A telescope like Chandra captures X-rays which are invisible to our eyes, but through this technique, the intensity of that light can become volume. A brighter, more energetic region of the remnant swells into a louder sound. The specific wavelength of the X-ray light can be mapped to a musical pitch, and the position of the source within the nebula shifts from the left speaker to the right, creating a three-dimensional soundscape. The result is not a random noise, but a structured composition that sweeps across the stereo field, allowing you to literally hear the expanding shell of stellar debris. This sweeping audio arc conveys the remnant's spherical structure in a way that is instantly intuitive, a ghostly chord that grows and evolves as your ears traverse the debris field from the center out to the edges. This is more than a novel way to experience data. It is a powerful analytical tool. The human ear is exceptionally good at detecting subtle patterns and rhythmic irregularities. A researcher staring at a complex visual map of a remnant might overlook a slight asymmetry, but their ears could pick up an imbalance in the sonic landscape, a lopsided swell in volume or an off-center pitch shift that reveals the hidden, chaotic nature of the original explosion. By listening to the data, scientists gain a new perspective, one that can highlight features lost in the sheer visual complexity of these cosmic wrecks. This process makes the invisible universe perceptible, translating the fierce, silent glow of million-degree gas into a form we can experience with another sense entirely. To hear the Tycho remnant is to feel its expansion, to perceive its structure not as a distant image but as an immersive event. It transforms a scientific dataset into a haunting melody, an echo from a star that died centuries ago, offering a deeply emotional and uniquely human connection to the violent poetry of the galactic graveyard. These silent, expanding ghosts are dissected by our greatest technological eyes in the sky. The Hubble Space Telescope captures the universe in visible and ultraviolet light, gifting us those breathtaking portraits of nebulae where we can trace every delicate filament. Its sharp vision reveals the intricate shock structures sculpted by the collision of the stellar debris with itself and the surrounding space, painting the optical beauty of the reverse shock. But to see the true violence, we must look with X-ray eyes. The Chandra Observatory specializes in this high-energy light, detecting the fierce glow of gas heated to millions of degrees. Chandra's view cuts through the visible spectacle to show us the scorching hot heart of the remnant, the regions where the forward shock wave is still slamming into the interstellar medium, and where the neutron star or black hole pumps energy into its surroundings. Then there is the infrared perspective, championed by the now retired Spitzer Space Telescope. Its infrared eyes acted like cosmic dust vision, peering straight through obscuring clouds to see the cooler material within the wreckage. Spitzer showed us where the heavy elements were condensing into new, solid dust grains, the very seeds for future planets forming on the ashes of the dead star. Alone, each telescope reveals a single chapter of the story, a ghost seen in only one color of light, but together they form a complete narrative. By layering Hubble's optical tapestry with Chandra's fiery X-ray core and Spitzer's dusty infrared veins, astronomers can perform a full cosmic autopsy. They can measure the total energy of the blast, decode the precise chemical composition of the ejected material, and track the transfer of energy from the central corpse to its expanding tomb. This multi-wavelength approach is our only way to read the entire life story of the star, from its death scream to its chemical legacy, and our vision is only getting sharper. The next generation of observatories, like the James Webb Space Telescope with its profound infrared sensitivity, and the Nancy Grace Roman Telescope with its colossal field of view, are already pushing this forensic science further. They are our time machines, pulling back the veil on these stellar graveyards with a clarity that would have been pure fantasy just a generation ago, revealing secrets from the deepest past written in the faintest light. For all the violence of a supernova, the initial collapse is strangely hesitant. When a massive star's core runs out of fuel, it does not explode immediately. It implodes, falling inward at nearly a quarter the speed of light. This collapse halts when the core becomes so dense it essentially turns into a solid ball of neutrons, creating the newborn neutron star. A powerful shockwave forms at its edge and begins racing outward, but within mere milliseconds it stalls. It runs out of steam, becoming a standing shockwave that cannot move forward, trapped by a relentless rain of materials still falling onto it from the collapsing star. This is the central puzzle, the supernova explosion mechanism problem. Why does this stalled shock suddenly revive and blast the entire star apart? For decades, our most powerful computer simulations have struggled to answer this. They can model the collapse, but they consistently fail to produce a successful explosion without us artificially adding a helping hand, a nudge of extra energy that is not fully understood. The leading suspect in this cosmic mystery is the ghostly neutrino. In the first second after collapse, the newborn neutron star is a seething hell of particles, and it releases an almost unimaginable flood of these tiny, nearly massless particles. The theory is that a small fraction of these neutrinos, maybe just 1 or 2%, are absorbed by the gas just below the stalled shock. This neutrino heating is thought to deposit enough energy to re-energize the shock, powering it like a cosmic engine and finally driving the explosion. But this process is incredibly delicate. It is not a simple spherical blast. Realistic simulations must account for a chaotic, churning madness inside the dying star. Convection bubbles of superheated gas rise and fall like a pot of boiling water, but on a scale of hundreds of miles per second. The star's rotation and its magnetic fields can twist this chaos into focused jets, turning a fizzle into a bang. The results are often marginal, a successful explosion in one simulation and a complete failure to launch in another, depending on minuscule changes in the starting conditions. Solving this problem means juggling the most extreme physics we know. It requires simultaneously modeling the warping of spacetime from general relativity, the complex interactions of nuclear matter, and the tricky paths of trillions of neutrinos as they bounce and scatter in the dense chaos. Cracking this code is the holy grail of computational astrophysics. Unlocking the precise mechanism would do more than just complete a chapter in a textbook. It would finally allow us to read the full story written in every expanding remnant we see, understanding not just the star's death, but the exact moment of its violent rebirth. This interstellar medium is the cemetery ground itself, the silent, invisible backdrop to every stellar ghost story. Far from being an empty void, the space between stars is filled with a wispy sea of gas and dust, a substance astronomers call the interstellar medium. This is the raw material of the galaxy, a mixture that is almost 99% gas, mostly hydrogen and helium, and 1% microscopic dust grains, finer than smoke. It is upon this vast, tenuous canvas that supernova remnants leave their most enduring marks, and it is this medium that gives the graveyard its ever-changing form. The interstellar medium is not a uniform fog, but exists in distinct and dynamic phases, a cosmic ecosystem of its own. There are vast regions of million-degree hot gas, blown clear by ancient supernova bubbles. There are warmer zones of neutral hydrogen, and there are deep, frigid clouds of molecular gas, so cold and dense that atoms can link together to form complex molecules. The primary engine that heats this gas and churns it between these different phases is the supernova shock wave. When a remnant expands, it injects colossal energy into its surroundings, violently heating the thin gas and stirring the entire galactic pot. This creates a turbulent, self-regulating environment where the death of one star directly shapes the conditions for the birth of the next. The interaction is most poetic when a remnant shock front slams into a pre-existing, cold cloud within the interstellar medium. The shock acts like a cosmic hammer, crushing the cloud and compressing the gas. This sudden squeeze can overwhelm the cloud's internal pressure, allowing gravity to finally take hold where it could not before. In this way, a wave of destruction becomes a catalyst for creation, triggering the collapse of a gas cloud and igniting the fire of new stars. This process, known as triggered star formation, directly links the end of one stellar generation to the beginning of another. Within these cold, dark clouds, the dust grains of the interstellar medium play a surprisingly vital role. These tiny particles, many forged in the atmospheres of previous generations of stars, act as miniature platforms. They provide a solid surface where lone atoms of hydrogen can meet, stick, and slowly build up into molecular hydrogen, the primary fuel for star formation. Furthermore, this cosmic dust provides a crucial shield. It blocks the harsh, energetic ultraviolet radiation that floods interstellar space, radiation that would otherwise tear fragile molecules apart. This protective dust allows rich chemical factories to thrive in the darkness, creating the complex organic molecules that may one day be incorporated into new planetary systems. The very composition and patchwork structure of the interstellar medium we see today is a direct result of countless past supernovae. Every element heavier than helium found within it was forged in a stellar core or a supernova blast. The bubbles, the filaments, and the varying temperatures are all the cumulative scars and gifts of these ancient explosions. The interstellar medium is more than a backdrop. It is a living, breathing archive, a graveyard where the dust of dead stars becomes the soil for new worlds. Deep within the beautiful chaos of a supernova remnant, a far more powerful engine is at work. These expanding shells of debris are nature's own particle accelerators, operating on a scale that makes our most powerful machines on Earth seem utterly insignificant. They are the primary source of cosmic rays, a constant rain of high-energy particles, mostly protons and atomic nuclei, that silently sleet through the galaxy and bombard our own planet. The mechanism that creates them is both elegant and relentless, a process known as diffusive shock acceleration. Picture the remnant's forward shock wave, a supersonic wall of energy plowing through space. A lone proton caught in this turbulent frontier does not simply get swept along. Instead, it becomes trapped, bouncing back and forth across the shock front like a pinball. Each time it crosses that boundary, the magnetic fields embedded in the shock give it a slight boost, a tiny kick of energy. Over and over it ricochets, gaining speed with every pass until it is finally flung out into the depths of the galaxy, traveling at nearly the speed of light. We have direct evidence for this incredible process written in the light these remnants emit. When these newly minted cosmic rays, now traveling at fantastic speeds, collide with atoms of gas in the surrounding cloud, they produce flashes of gamma-ray light. Our telescopes can detect this high-energy signature, a clear fingerprint of the acceleration process in action. Furthermore, the ultra-relativistic electrons within the remnant spiral along its tangled magnetic fields, giving off a specific type of X-ray glow called synchrotron radiation, painting the nebula with the light of its own incredible power. The efficiency of this cosmic factory is staggering. A single supernova remnant can convert a significant fraction of its total explosive energy, itself an almost unimaginable quantity. into these accelerated particles. This means the galactic graveyard is not just a place of quiet rest, but a vibrant, energetic power plant, continuously flooding the Milky Way with these invisible, high-speed projectiles. This has profound consequences for the entire galaxy. These cosmic rays help ionize the gas in the vast molecular clouds where new stars are born, influencing the very process of star formation. They may even play a role in the complex chemistry that leads to the formation of planets, their subtle energy potentially helping to forge the prebiotic molecules that are the precursors to life. Every second, countless particles born in these stellar graveyards pass straight through you, silent, invisible messengers from a ghost that died thousands of years ago, a constant reminder of the dynamic and powerful universe we inhabit. Our view of these cosmic graveyards is about to become sharper than ever before. A new generation of telescopes is poised to transform those faint, ghostly blurs into detailed astrophysical laboratories, revealing secrets we have only been able to guess at until now. The James Webb Space Telescope, with its profound infrared vision, acts as a cosmic dustbuster. It will peer straight through the obscuring veils of gas and dust to see the very heart of supernova remnants, analyzing the complex chemistry happening within. It will show us where newly forged elements are cooling and condensing into the first solid dust grains, the primordial seeds for future planets, all forming on the ashes of the dead star. Alongside it, the Nancy Grace Roman Space Telescope will function as a master cartographer of the dead. Its incredibly wide field of view will allow it to conduct vast surveys of the sky, discovering and cataloging thousands of faint, ancient supernova remnants that have until now remained hidden. It will build the first complete census of our galaxy's stellar graveyards, revealing the full scale of this cosmic cycle of death and rebirth. On the ground, the colossal eye of the extremely large telescope will provide a level of detail that was once pure fantasy. With a mirror nearly the size of a blue whale, its resolution will be so immense that it could potentially distinguish a car's headlights on the surface of the moon. It will study the fine, tangled structure of remnants in visible light, watching the shock fronts themselves expand in real time and mapping the complex motions of the gas with breathtaking precision. To understand the violence, we will turn to a new generation of X-ray observatories. The European Space Agency's upcoming Athena mission will be a powerhouse for high-energy astronomy. It will map the scorching, million-degree gas within remnants with exquisite spectral resolution, acting like a cosmic chemist's scalpel. It will not only identify every element present in the stellar debris, but also measure its exact temperature, density, and velocity, showing us how this enriched material is churning and mixing as it flies outward. These are not just incremental improvements, they represent a fundamental shift in our perception. We are moving from simply seeing these ghosts to truly understanding their anatomy, their life history, and their ultimate role in shaping the galaxy. With these new eyes on the sky, we stand at the threshold of a new era, ready to read the deepest secrets still hidden within these cosmic tombs. These cosmic engines of destruction are also galleries of sublime beauty. The ghostly remains of a supernova are not just scientifically rich, they are visually breathtaking, their intricate filaments and ethereal shapes painted across the void. The iconic pillars of creation, though a stellar nursery and not a remnant, perfectly illustrates the artistic potential of cosmic gas and dust, where light sculpts and illuminates vast structures. But for a more direct vision of stellar death, look to the Crab Nebula. Hubble's portrait reveals a tempest of glowing material with a central heart of brilliant blue light, the synchrotron radiation from electrons spiraling near light speed, all woven through with fiery red filaments of energized oxygen. Or consider the Veil Nebula, a sprawling lacework of gas so delicate it seems it might dissolve at a touch, each thread a testament to the shockwave's intricate passage. This is not random splendor. Every color tells a chemical story. The vibrant reds often glow from excited sulfur and nitrogen, the rich greens from oxygen, and the faint blues from hydrogen, each element heated to luminescence by the relentless energy of the expanding blast wave. This artistic connection is not reserved for powerful telescopes alone. An amateur astronomer with a modest backyard telescope can point towards the Cygnus loop and see a faint, filmy veil of light, a direct visual link to a cataclysm that occurred thousands of years ago. That ability to witness a stellar ghost with our own eyes, or through the shared images that have become cultural touchstones, serves as a powerful gateway. The beauty pulls us in, and the science holds us, telling a story of elemental creation and cosmic recycling. The haunting elegance of a supernova remnant is the universe's most poignant paradox, a celestial phoenix whose death is a canvas for its most stunning art. That sudden, brilliant star in the ancient sky was never just a point of light. It was a story waiting to be told. Long before telescopes could dissect their physics, supernovae were woven into the fabric of human culture, interpreted as divine messengers or terrifying omens. Some historians and astronomers have pondered a compelling possibility that the Star of Bethlehem which guided the Magi could have been a supernova, a new and brilliant light heralding a new age. This celestial drama was not always a welcome sight. For many cultures it signaled the death of an emperor, the outbreak of war, or a coming famine. The very unpredictability of these stellar guests made them powerful symbols in a world where the heavens were thought to be perfect and unchanging. This ancient awe has seamlessly transitioned into the modern era, where supernovae fuel our science fiction. In Arthur C. Clarke's haunting short story The Star, a group of space explorers discovers the remnant of a supernova that annihilated a beautiful, advanced civilization, forcing a profound confrontation between faith and cosmic indifference. Carl Sagan, in his seminal series Cosmos, used the supernova not as a destroyer, but as a creator, eloquently explaining how we are all made from the ashes of these great explosions. The term itself has exploded into our everyday language. We speak of a pop star's career going supernova, a brilliant but brief peak before fading from view. A company might be described as a supernova in its industry, burning impossibly bright before a sudden collapse. This linguistic adoption reveals a deep, intuitive understanding of the phenomenon, a brilliant and terminal climax that captures our imagination. These stories, both ancient and modern, serve a profound purpose. They are a bridge across time, connecting the human who looked up in wonder and fear at a new star with the human who points a telescope at its expanding ghost. They transform a distant astrophysical event into a mirror for our own existential questions about creation, destruction, and the legacy we leave behind. The supernova reminds us of our small place in a vast and dynamic universe, a realization that can spark both existential dread and inspirational awe in equal measure. The cosmic graveyard reveals its most intricate secrets not in solitary tombs, but in the lingering dances of the dead. When a massive star explodes within a binary system, its death is not a private affair but a violent event that forever alters its partner. The supernova explosion is rarely symmetrical, and this lopsided detonation can deliver a powerful kick to the newborn neutron star, a gravitational slingshot that sends the stellar corpse flying. In some cases, this kick is so violent it flings the neutron star clear out of the system entirely, creating a runaway ghost hurtling through interstellar space alone. In other scenarios, the binary bond survives but is stretched and warped, leaving the neutron star in a wide, lopsided orbit around its still living companion. This celestial drama sets the stage for some of the most energetic and bizarre objects in the galaxy. If the stars remain close, the stellar corpse can become a cosmic vampire. In a system known as an X-ray binary, the immense gravity of a neutron star or black hole begins to siphon gas directly from its companion. This stolen material doesn't fall in silently. It spirals down into an accretion disk, a vortex of superheated plasma that glows with ferocious X-rays as it is consumed, a brilliant beacon of one star feeding on another. Even more profound are the double neutron star systems, where both stellar corpses are locked in a frantic orbital embrace. These systems are so precise, so predictable, that they became the universe's first gift to the science of gravitational waves. By meticulously tracking the orbital decay of one such pair, astronomers confirmed that the system was losing energy exactly as predicted if it were radiating these ripples in spacetime, providing the first indirect proof of Einstein's prediction. This dance, however, always ends in a cataclysm. The orbits of these binary neutron stars slowly decay over millions of years, drawing the two ultra-dense objects closer and closer until they finally merge. In 2017, the LIGO Observatory felt this final embrace from a distant galaxy, detecting the chirp of gravitational waves as two neutron stars spiraled into each other. The collision was a spectacle of cosmic alchemy. It produced a short, intense flash of gamma rays and, in the turbulent debris, forged the heaviest elements in the universe through the rapid neutron capture process. The gold in your jewelry and the platinum in a catalytic converter were likely born in such a violent merger. These binary graveyards are the ultimate cosmic laboratories, places where we can study the limits of gravity, the physics of extreme accretion, and the very creation of matter. They prove that a star's social life does not end with its death, and that the most profound creations often arise from the most intimate and destructive of celestial partnerships. For all the intricate maps we have charted and the violent histories we have reconstructed, these galactic graveyards guard their deepest secrets with a silent resolve. We still do not know the precise moment a star's dying heart finally reignites its own destruction. The exact explosion mechanism for a core collapse supernova remains one of the great unsolved puzzles in all of astrophysics. Our most powerful computer simulations continue to struggle, often requiring an artificial nudge to make the star explode, leaving us to wonder what final, critical piece of physics we are still missing from that chaotic inner storm. This fundamental uncertainty is mirrored in the origin of the universe's most powerful particles. While we know supernova remnants are fantastic particle accelerators, the precise source of the very highest energy cosmic rays, those with energies far beyond what our largest colliders can produce, is still a topic of intense debate. Are they born in the shock waves of the youngest, most violent remnants, or could they come from something even more exotic, like the mergers of neutron stars or the hearts of active galaxies? On a galactic scale, the questions only grow more profound. Astronomers are fascinated by a class of small, intensely green galaxies nicknamed green peas. These distant objects are undergoing ferocious bursts of star formation, and with that comes a hailstorm of supernova. The role of this supernova feedback, how these explosions collectively heat the gas, drive powerful winds, and ultimately regulate the growth of the galaxy itself, is an active and crucial area of research. It forces us to ask how much of the cosmic dust, the very stuff of future planets, is actually forged in a supernova's furnace versus how much is simply vaporized by its fury. We are still weighing the creation against the destruction in these events. Even the final act of the most massive stars is not a settled script. For stars of a certain immense size, does death always come with a brilliant supernova flash, or can a star simply collapse in on itself in a silent, dark implosion, skipping the explosion entirely to form a black hole? The answer would tell us how many of these dark tombs might be hiding in our galaxy, completely unseen. This leads directly to the mystery of the orphans. The population of neutron stars and black holes that received such a powerful kick at birth that they now wander the interstellar darkness alone, untethered from any remnant or companion, is a number we can only guess at. They are invisible ghosts drifting through an invisible sea. Ultimately, the role of supernova stretches across cosmic time, shaping the evolution of galaxies from the early universe to the present day. How did these explosions contribute to the large-scale structure of the cosmos, helping to clear vast voids and sculpt the great filamentary walls of galaxies we see today? This complex feedback loop, where stellar death dictates the conditions for stellar birth on a galactic scale, is a puzzle we are only beginning to piece together. Yet these enduring mysteries are not failures of understanding. They are the very engines of discovery, the unanswered questions that will drive the next generation of telescopes and theorists to look deeper, think harder, and continue listening for the whispers of these stellar ghosts. The graveyard is not a closed book but a living library, and we have only just begun to read its most profound chapters. Our journey through these stellar tombs reveals a universe built on cycles of death and rebirth. From the violent flash of a supernova to the beautiful, glowing nebula it leaves behind, and onward to the bizarre reality of a city-sized neutron star, we have traced the life cycle of cosmic matter. These events are far more than spectacular endings. They are the universe's essential engines of change. They forge the very elements that compose our bodies and our world. They stir the galactic pot to birth new stars, and they create environments so extreme they challenge the laws of physics. A supernova remnant is not merely a grave, it is a cradle, a place of destruction that makes all future creation possible. We are living proof of this deep connection. As Carl Sagan so eloquently reminded us, the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, and the carbon in our food were all forged in the interiors of collapsing stars. We are made of star stuff. Let this profound truth fill you with a deep sense of wonder the next time you gaze at the night sky. Look up and consider those silent, beautiful graveyards scattered across the darkness, knowing that you are their most remarkable product. If this journey into the cosmic afterlife captivated you, subscribe for more explorations into the universe's greatest mysteries. We would love to hear your thoughts on these stellar ghosts in the comments below.